Okay, great. Alena, are you okay if I do the introduction and then we start?
Yes.
Cool, perfect. Then thanks everyone for joining us today. Today we are glad to have Alena giving a talk about her paper, StaQ, Growing Neural Network for Policy Neural Descent. Alena is a researcher at INRIA StaQ in Paris, working at the intersection of reinforcement learning and scientific machine learning. In particular, as you can guess from this talk, now she's exploring growing neural for and with reinforcement learning. Previously, she was a postdoctoral researcher, always at INRIA, but in Lille, and she completed her PhD at INRIA Bordeaux. Thanks a lot, Alena, for accepting our invitation, and the stage is yours. Thank you again.
Thank you, Luca, for a nice introduction, and thank you for inviting me for a RL theory seminar. It's quite an honor for me, also considering that I'm not considering myself as theoretician, so it's quite nice to get such recognition. And so today I will present a paper called StaQ, Growing Neural Networks for Policy Mirror Descent. And this work will not be possible without my collaborators, such as Alex Davis. She's present online, I see her. And also by Brahim Driss and Riyad Akro. So actually, all of us were very well involved into this paper, which we're working on actively, like roughly 1 year ago. And so let me now start. Do you see well my slides? Okay. So our paper falls into the setting of entropy regularized reinforcement learning, and we consider of finding the optimal policy for Markov decision processes. So a reminder, for Markov decision processes, models the interaction between the agent and the environment. Typically, at each iteration, the agent sees the current state of the environment, and following some policy, decides which action to choose. Once the agent applies an action A, it receives the reward signal from the environment and the information about the next state. So as we are interested in the entropy regularized RL, our objective, our optimization function, is to find such policy that maximize the value function that is parameterized by the policy pi and the tau, where tau controls the entropy bonus. So value function thus represents the cumulative reward accompanied by the entropy bonus. So I don't know if you see my arrow. Yes, the entropy bonus is added to each reward individually. So this is typically the negative entropy, and the motivation for that is to prevent typically the early conversions to the deterministic policy that exhibits some suboptimal behavior. And in general, people observe that adding such entropy bonus encourages exploration and robustness of the training. Our paper falls into the more like policy iteration setting. So a reminder, what this policy iteration algorithm is doing. So it alternates between the two steps, mainly the policy evaluation. So where we, given the policy pi k, we are trying to approximate or to find what would be the Q function associated to the policy pi k. So reminder, function Q function is defined through the value function by taking the reward and the expectation on the value function on the next state. And once we evaluated our policy, we update our policy, we obtain the next policy pi k plus 1, and we repeat these steps until we get to the policy pi star. That should represent the optimal policy that is associated to the optimal Q value function. So in what follows, we will assume that for any given policy pi, we can evaluate Q function associated to policy pi without an error. Of course, it's quite it's not realistic in practice. So we will address also like how to mitigate the error as well. But for now, let's assume that we can do it precisely. And the question now that we would like to ask, so if we don't have an error on the policy evaluation, how can we update the policy function in such a way that we don't have an error as well? So for that, we will use the formulas of mirror descent. So I don't know if you're familiar with mirror descent, but if we consider classical gradient descent, where classical gradient descent solves the minimization problem of our, like here we minimization setting. So if we want to minimize our function f with respect to the point x, so the classical gradient descent would be equivalent of like finding the next point in which the linearization of our function f at the point xk achieves the minimal point, and at the same time, for this linearization to hold, we need to constrain that our point x doesn't go too far from some reference point xk. Thus, we add this regularization term. So in case of gradient descent, this is classical Euclidean distance, but we can generalize it to a more another metric representation. So typical choice would be choosing the Bregman divergence. So Bregman divergence, given the function h, which is typically strongly convex, measures the distance between the value of function h in the point x and its linearized representation. So this distance is summarized here in the bottom right picture. And thus, for different choices of h, it gives us different choices of somewhat pseudometrics. And if we choose h to be just a square of our norm with respect to x, then we retrieve our classical gradient descent. But if we choose h to be the negative entropy, the Bregman divergence becomes Kullback-Leibler divergence. And so that's what we'll use in the next slides. So again, we would like to maximize the value function. And as we know, that's the gradient of the value function with respect to policy is proportional to Q function. After simplifying a bit after plugging this gradient into the mirror descent formulation presented in the slide before, and simplifying some terms, we can retrieve this simple optimization problem mentioned in equation 5. So here, to get the next policy pi at the step k+1, we would like to find the policy p such that maximize the dot product between Q function and p minus negative entropy minus Kullback-Leibler divergence, where we measure the distance between like unknown policy p and the reference policy pi k. So this optimization problem is a constrained optimization problems, and it has an analytical solution. If we like just apply a standard argument using Karoshi-Kuhn-Attacker, we can retrieve the closed form solution for our next policy at the step k+1. So this is given in equation 6, and we see that our policy at the step k+1 depend on the mixes, the previous policy at the step k, and the exponent of the Q function evaluated at the also previous step k. And it mixes it with different values. So this value we will denote as beta, and this value we will denote as alpha. So it brings us to this more simplified formulation. We can unroll this equation 6, so such that we get rid of the dependence on the previous policy pi k. And after unrolling this recursion, we retrieve that policy at step k should be proportional to the exponent of the sum of all weighted, weighted with discount beta of different policy evaluation Q pi k. So thus we have like, if we able to compute exactly this sum and then take the exponent of this, we obtain the exact policy update. And we can observe that this update encompasses many popular deep REL algorithms. Indeed, when we take eta to 0, we set eta to 0 and alpha then becomes 1 over tau, and beta becomes 0. In this case, if a policy is approximated through the policy network, then it's soft autocritic. If we use a precise formula, then it's Munchausen DQN. On the other hand, if we set tau towards 0, then alpha becomes 1 over eta, and beta becomes 1. So we get the undiscounted sum of all the Q functions. So in the exact formulation, this is Polytech. And in the approximated case, when we approximate the policy with a policy network, it's TRPO or PPO. So for this exact policy update, we actually know the convergence result. So here in this slide, we presented the theorem, which we readapted from Jean et al. From 2023. So we can see that QK will converge to the optimal Q function with the speed d, where d is the beta plus gamma multiplied by 1 minus beta. So typically d is less than 1 because it's interpolates between 1 and gamma with a weight beta. And this convergence speed is applied to the this inner term, which depends on the initial error, like of our initial Q function respect to optimal Q function, and the norm of the optimal Q function. Despite convergence guarantees, computing in precise way policy by k, which depends again on the sum of all the past Q functions, is intractable for large k. And indeed, it's easy to see that in tabular setting, it requires storing the k matrices of size S times A. In case of neural networks, we need to store k separate neural networks. So as we can imagine, if we want to apply this algorithm for Atari, where typically we do like 50 million of steps to converge, this will require 50 million neural networks, which is non-realistic, even if you have a very advanced hardware. But we can observe that if beta is less than 1, then the contribution of all the most oldest Q functions becomes negligibly small. So with the time, the contribution of all the Q function becomes smaller and smaller because beta becomes they are punished by the beta to the large power. Thus, here comes the idea and question, can we create a finite memory algorithm by dropping old Qs? So when I say finite memory, so instead of letting adding into our ensemble indefinite number of Q functions, we just say that we only add m Q functions and not more than this. And so now here comes our first contribution. In particular, we propose what we call vanilla finite memory EPMD, which exactly reflects this idea. So if in the exact EPMD we have the sum from 0 to k, and our logits, so logits, it's the term on the exponent in our distribution, is the sum of all the past Q functions, which in recursive formula is represented like this. So the logits of the new policy is the mixing between the logits of the previous policy plus the Q function related for the previous policy. Then for the fixed memory size m, at each iteration, when we add a new Q function, we also delete the old Q function in our logits representation. So here, this term represents the deletion of the oldest Q function in our finite memory buffer. And thus, here the sum becomes truncated. So instead of going up to k, we go up to m minus 1. So now this only depends on the last MQ function. And we have a convergence result that states that for large finite M, our vanilla finite memory EPMD converges to a small error of order b2 power m. But we keep the same convergence speed, which is expressed as the variable d, which mixes between gamma and 1 with the weight beta. So let me guide you through the main steps of the proof. We will further reduce the same steps for our second theoretical contribution. So in order to obtain the above convergence result, we first present like a more general result that we call approximate policy improvement, that formulates the policy improvement with some penalization that depends on the drifting of our reference policy. When I say drifting of our reference policy, it means that now, instead of solving, so I don't know if you remember exactly the formula of the previous PMD, of the exact PMD, but the exact PMD before was obtained by solving this optimization problem, where here was the true previous policy. But now we don't have the access to the true previous policy, and instead we have like kind of truncated policy, which we denote as pi k tilde. So what I will further refer as a drifted policy. And thus, instead of dealing with instead of expressing the logits of the new policy through the logits of the previous policy plus Q function, we express it through the logits of this drifted policy. So here we plug a CK tilde. And so what our approximate policy improvement theorem states is that our Q function at each iteration k plus 1 improves over previous Q function, but with some penalty that is proportional to the difference between the policy, the true policy pi k, and the drifted policy pi k tilde, and the difference in terms of their logits. So the logits of the previous policy pi k and the drifted logits CK tilde. Yes, I see the raised hand.
Yes, sorry, I wanted just to ask something about the drifted policy. The logits, do they have the subtraction of the last Q function as you were mentioning in the previous slide?
Yes, so like here we just talk about general drifted policy, but in the particular case of vanilla finite memory, EPMD, that we'll see in the further slides, we will see that we have an exact formula for CK tilde, and this is obtained indeed by taking CK and by subtracting from CK the deletion.
Okay, sorry, I didn't notice that this result is kind of for any pi tilde and
so because we plan to reuse this result for further. That's why I presented it for more general.
Thank you. Amazing.
Okay, and so this result is indeed presented for more general pi k tilde, such that our new policy pi k plus 1 is obtained by solving this optimization problem. So I hope this part is clear. So we see that this theorem basically shows that policy improvement is now formulated through the logit difference somehow. Like we see that we have dependence on this term. So here is the sketch of the proof. Actually, it follows quite a standard arguments for the policy improvement. So before going forward, like let me introduce our Bellman operators. So one defined through the policy pi. So we here see the formula of first Bellman operator, and but the only difference with maybe classical formulations that we have this entropy bonus here, and we also define the Bellman optimality operator T star. So again, here we plug the maximum over P, and we also keep our entropy bonus here. So both operators rely on such properties as monotonicity, contraction, fixed point existence. So like quite standard properties. And so important step of this theorem is to show that the Kullback-Leibler divergence between pi k and pi k tilde actually can be upper bounded by the difference between pi and pi tilde and logits, the difference in their logits. So psi and psi tilde. And thus, by taking epsilon being equal to the eta and the maximum of over S of a norm of pi minus pi tilde in the first norm, and the difference between logits in the infinity norm, then we can see that the application of the Bellman operator associated to the previous policy, to our previous Q function, is less than equal than application of our Bellman operator for the next policy to our previous Q function, plus the penalization term like gamma epsilon. So, and then following standard arguments, but by repeating this basically inequality many steps, we can retrieve and also using the fixed point existence, we can retrieve the statement of the theorem. But we can see that the gamma epsilon is actually coming from the drift, let's say, in terms of policy between the true policy pi k and pi k tilde. So now let's apply this approximate policy improvement for our vanilla finite memory EPMD. So as I already mentioned for Luca, so that xi k tilde has a explicit form through the ck. So we take ck and we just delete our oldest q function in our memory. So qk minus m tau. And thus we obtain that's our policy improvement result for vanilla finite memory PMD. So we see that our penalization term scales as beta to power m and some norm upper bound on the Q function, on the norm of the Q function. So this term comes exactly by applying the infinity norm on the difference between the logits. So by plugging this expression here, we see that it can be upper bounded by beta to power m and some bounding constant r overline. So let's continue to the next step of the convergence theorem. So another intermediate result that we proved, it's the lemma that states that's actually convergence of our Q function with respect to the current policy pi k plus 1 can be expressed through the convergence of the tau multiplied by the logits of our current policy. So it will converge only if this term will converge. So to obtain this inequality, we just do quite standard arguments by considering that the qk plus, so the difference between the Q function associated to the current policy and the optimal Q function can be decomposed into two elements. So one that is dependent on the application of the optimal Bellman operator to our optimal Q function and the logits tau ck plus 1. So this is can be quite easily shown by using the property that policy at the next step k plus 1 is actually maximizing this quantity, so like the dot product of the logit minus the negative entropy. So can be seen as a legend, I forgot the name, Fenchel conjugate. Yes, and then the second term that actually depends on the difference between the current Q function and the tau ck plus 1 can be upper bounded by some term that depends on beta, m, epsilon, and the r, which is like the upper bound of our Q norm. By applying triangular inequality and contraction property of the Bellman optimality operator, we retrieve actually the statement of our lemma 1. So the only thing left to show the convergence is to show actually the convergence of our logits, like multiplied to tau, to the optimal Q function. For that, we first apply triangular inequality. So we decompose our difference respect to the difference for the previous logits. So here it's the logits for the step k plus 1, and here it's the logits for the step k. And also the difference of the optimal Q function with respect to Q function from the previous step, plus a term that depends on the norm of the Q function that is the oldest Q function in our memory. So then by reapplying lemma 1, because lemma 1 gives us exactly the dependence of this term with respect to this term, then we can observe, we can get some kind of a recurrent rule for how our difference of logits respect to the optimal Q function changes over k. And here we can indeed retrieve our typical convergence speed from the exact policy mirror descent. plus the constant that depends on epsilon, beta, gamma, and m. So by repeating it k times, we get the final convergence result. Thus, vanilla finite memory EPMD shows the same convergence speed as the exact EPMD, but this only holds up to some constant error of order beta to the power m. So beta to the power m, even if it's small for large m, it's still irreducible. And this brings us to the second theoretical contribution of our paper. It's actually how to mitigate this error. And for that, each time, so instead of only deleting our oldest Q function, we actually replace the oldest deleted Q function with the most recent one. So we have a deletion and plus re-adding the second time, let's say, our current Q function, but with some weight. And this weight is proportional to 1 over 1 minus beta m. So intuition behind this update is that if we assume that we are in the latest iteration of our algorithm and everything goes well and our Q function converge and they converge to the optimal Q function, then if we plug this expression in the vanilla EPMD, so if we try to understand what is the state of our logits multiplied by tau with respect to the Q star, so we just plug the formula for logits from vanilla EPMD, and we obtain something that is equal to 1 minus beta to the power m to the multiplied by optimal Q function. So we see that the logits don't converge to the optimal Q function, while in the weight-corrected EPMD, so if we plug this formula here, we see that as a Q star is constant, so we can remove it from the sum. And then the only thing left is the sum of geometrical series, and we know exactly what is the sum of geometrical series. So it would be this term. And this term is cancelled with the term in front. And thus, we retrieve exactly the optimal Q function. So already empirically, we see the advantage of weight correction. I don't know if you have questions here before moving to proofs. Okay, good. So, and first we can prove for weight-corrected finite memory EPMD that we can converge to an error-free policy improvement for large enough M. Mainly, we state that there exists such M that is larger than this, I don't know, very ugly expression, but it has quite, that depends on gamma beta. And if M is larger than this critical value, then we can show that the Q function for policy pi k, as iteration progress, will converge to the optimal Q function with the speed d prime, where d prime is less than 1, and it depends on gamma, beta, and m. And moreover, at the m going to infinity, we retrieve our classical convergence speed, which is d. So just before moving to the proof details, just to show that this critical value actually is making sense in practice, we try to plug in directly the typical values from the practical DeepRL algorithms, such as gamma equal to 0.99 and beta equal to 0.95. And we have got that after m, so with m starting being larger than 265, we get the convergence. And thus in our practical algorithm, which I will show at the end of presentation, we used m equal 300 for almost every execution. So now let's move to the proof. So again, we will reuse the result that we discussed before, the approximate policy improvement. So for that, we just need to understand what is our drifted policy in the case of weight corrections. So here, the logits of the drifted policy I expressed through this expression, where we see it depends on the difference between the most recent Q function and the most oldest Q function in our memory. And thus, once we plug this result into our approximate policy improvement, we get this penalization to our policy improvement, which we see that it scales as the difference between the the norm of the difference between the most recent Q function and the most oldest Q function. Thus, if Q converges, that we hope it converges, then this term becomes small. Then we prove also the lemma 2. So lemma 2, it's like the analogy of lemma 1, which express the convergence of Q function to the optimal Q function through the logits, through the convergence of the logits towards the optimal Q function. But now in the weight-corrected finite memory EPMD case. So we see this term appear again, but now with the difference that we have this term that depends. So it's a sum of all the different epsilon k prime with a discounted weight beta, where epsilon k prime we see depends on the norm of the difference between the recent and oldest Q functions. So the proof follows the same steps as lemma 1, but now epsilon k prime depends on how the added Q term is different from the deleted one. Then another ingredient that we need to prove our convergence result is introducing the upper bound in sequences. So let's assume that there is some quantity xk that can upper bound the difference between qk, so the Q function at the step k, respect to the optimal Q function. So let's assume that all the upper bounds are denoted as xk. Then we can show that those upper bounds can follow quite a simple recursive rule expressed through here. So each new bound will depend only on the bound from the previous step k and the step that is associated to the oldest Q function in our memory, so at the step k minus m. So to prove this recursive formula, we just reuse the result from lemma 2, where we analyze each term separately and express it through different x, the upper bounds. So for example, the first term will be a different summations of x's associated to all the x's for the Q functions in our memory, present in our memory. So it's roughly expressed as the same formula as we saw for the logits itself. Then epsilon k prime that we saw in the previous slides that scales as the norm of the difference between the added and the deleted term depends only on the most on the previous xk and on the xk at the x at the step k minus m, and so on and so on. And when we plug those upper bounds in the equation 30 so in the lemma 2, this gives us, and after simplifying of course the terms, it gives us a recursive definition of xk plus 1 that we should see in equation 31. And now we are ready to give the convergence result for our weight corrected version. So first we show that for some large m, so where here you recognize the ugly formula from the theorem statement. So for large m, we can see that the different coefficient that mixes our upper bounds, the sum of them would be less than 1. So, and this in turn implies that our upper bound in sequence is a decreasing sequence. And we know it's a decreasing sequence that is also low bounded by 0. So no, all the xk should be larger than 0. Moreover, we also analyzed its subsequence, and we noticed the subsequence converges to 0, thus the whole sequence converges to 0. And now we need to characterize the convergence speed of this upper bounding sequence. For that, we take again the formula, recursive formula given here. And we, let's say, unroll the definition of xk minus 1. So we reapply this recursive formula, but for all the xk minus 1. And thus we retrieve all the sum of all the x's associated to different Q functions from our memory. And as we know that x is a decreasing sequence, thus we can lower bound this term by taking the x at the step k minus m. And thus we can retrieve like a common term that we will denote as D3. Now that we define what is D3, we can return again to our recursive formula given here. But now what we'll try to do is get rid of dependency on the xk minus m. And for that, so we just add xk with the term d2 multiplied by d3 to power minus 1, and we subtract it as well here. And we see that if we reuse the inequality obtained in the formula 33 here, we will see that this term, so this becomes 1, and this will get cancelled by this term, and thus we will get on dependence on xk. And where now this characterizes the speed of our convergence. And so by repeating it multiple times, we retrieve how the upper bound depends on the initial error of our initial policy pi 0 with respect to optimal policy. And so this term is easy to show that for our critical value of m should be smaller than 1. And thus, we know that as xk upper bounds the difference between q function at the step k and the q star, so the optimal q function, and it converges to 0, then we basically get our convergence results. So this is the end for our theoretical proofs. Just a small comment is that in case when the q function is not computed perfectly, so like when we actually have some policy evaluation error, it's not too difficult to extend our previous convergence results to also the case where we assume the bounded evaluation error, mainly if we act on the q tilde k tau, where q tilde k tau is not too much different from the true qk tau, and this difference is upper bounded by epsilon eval. And thus, the convergence results that I presented above will only update it with this error. So it will hold, but up to this error that depends on epsilon eval. So if epsilon eval is 0, then we get no error. But of course, if there is policy evaluation error, we get some error. But this is quite similar to another literature that we observed that works on the policy mirror descent convergence. And more recently, our results were extended to an iteration-dependent error. So when different q tilde k tau, for different iteration k, we get the different errors epsilon k. And so for now, I think it's not published yet, but it will just stay tuned, and we will update our archive version to include this result as well. Okay, so now that we passed through the theoretical contributions, now let me explain you how we implemented actually this idea in practice. So now, as we have now our policy, it's the ensemble of all the past Q functions. So which typically we keep M past Q function. Thus, if all those past Q functions are neural networks, typically what we do is that we tensorize the forward passes of all those neural network into one operation. And thus, it's equivalent to stacking those Q function in one big tensor, let's say. And as it's stacked, it allows us to compute the forward for all those Q functions in our memory in parallel, and thus results in quite reasonable training time for the whole stack. And then our algorithm is following quite standard steps for policy iteration. So first we collect our data by rolling out our behavioral policy. So in all algorithms, we choose our behavioral policy to be like a sort of what we call absence of max policy, which takes a random action, random uniform action with probability epsilon, and otherwise it takes an action from our stacked policy pi k. And after collecting data, we do policy evaluation step that we perform with fitted Q iteration, thus by minimizing the Bellman error. And then we do policy update by just adding the new Q function, the new evaluation of the Q function to our stack, and we delete the oldest Q function from the stack. And thus we repeat these steps all over again until we get something that looks like convergence. So let's see how it applies to some standard benchmarks from the DeepRL literature. So for our comparisons, we used what we call the discretized MuJoCo. So where we took a discretized action space on MuJoCo. We use quite straightforward strategy where for each possible action, we only consider extremal actions, in the sense that if we can move one joint, we freeze all other joints, so we don't apply any modification on the other joints. But for this particular joint, we either consider the max strength or the minimal strength possible. So either move in one direction or the other direction. And for each joint, we consider like the extremal actions defined like this. And thus we get the discretized MuJoCo. And we also consider min-atar environments, which is like atar environment, but more simple, with a more simple representation that are easier to learn. So in particular, we consider Asterix, Breakout, Freeway, and Sequest and Space Invaders. For comparison, we chose Munchausen DQN, TRPO, PPO, and natural gradient descent. And what we observe in practice is that overall StaQ shows quite improved performance compared to our baselines on almost all the benchmarks that we consider, and improved stability that here can be, for example, observed by having a slimmer error bars, like standard deviation bars for many environments such as Hopper, and humanoid, half cheetah, freeway. Of course, there is still some instability left, but I think it's already quite a positive feedback. And we also, interestingly, so here the vertical dash line represents the time when we start to delete the Q functions from our StaQ. So at first, when our StaQ is not full, we just keep updating Q functions. So it acts pretty much like exact PMD. But then after 1.5 million environment step, we start to delete those Q function following our weight corrected update. And we see that actually it doesn't have any negative impact on our performance. And actually, for many environments, our return keeps growing with iteration, despite that the StaQ keeps deleting the Q function. Of course, we did also an ablation study for the choice of M, so how much Q functions we actually keep in our StaQ. So we tried the M equal 1, M50, M100, 300. So 300 is our default choice, just to remind you. And of course, also larger choices of M, 500, and exact PMD. And we compared it with a natural gradient. And what we observed that starting from 300, it constantly, for all the benchmarks that we considered, it returns the best performances. And while M equal 1 is actually not too bad baseline, as we observe for some environments, it's still, for very complicated environments, it's exhibits quite degraded performance. So like as we see in the StaQ, M equal 1 is quite poor, also for Sequest, Space Invaders, and so on. So thus larger M is more important for more complex environments. And so now we come to the end of the presentation. Just before I finish, I would like to mention a few future directions. So we would like to add support for continuous action spaces. So for now, like the most straightforward way of doing this that we see, it's by adding a Nectar neural networks. But this will somehow we will get rid of our advantage of having policy error-free policy update in this case. So still we consider different options in this regard. We observe that for some environment, especially when we have a sparse reward, and in order to achieve the sparse reward, we need the kind of a coordinated behavioral policy and not just a random uniform policy. In this kind of environments, we observe that our StaQ may have problems to learn. And thus, further research on finding a more principal exploration behavioral policy rather than the default absence of marks that we consider should be still done in the future work. And also we wonder, do we actually need the M being so large, in particular 300, for the smaller problems? Because in general, what we observed that for some problems, M equal 1 was still performing quite well. So it seems like that our critical M is quite approximate. So probably we can improve on our estimation of the critical M in the future. And also what we would like to do is to have a closer look at policy evaluation to analyze how to mitigate this policy evaluation error. And also what we were thinking about, also to apply a StaQ-like learning, but for learning an individual Q function, which can be seen as doing kind of a gradient boosting approach, but when you learn just individual Q function. So you learn some initial representation, you measure the error, and then you measure what a new representation you should learn that minimize this error, etc., etc. And so this is like the end of my presentation. Thank you for your attention. So if you have any question, I will be happy to answer.
Great. Thank you so much for the talk. Yeah, David, go ahead.
Oh, it's more of a comment. I have to admit that I found the first part of the talk that was theoretical, so it was done on in the tabular setting, very confusing, thinking all the time, but I can just add the Q functions. Why do I want to throw any of them away, right? I could just add them in one table. I don't need any more memory. But of course, the point is that with neural networks for which you want to apply, yeah, this no longer works. And now the question, when you're thinking about continuous action spaces, how would you go about sampling from your policy? Have you got a plan for that?
It's actually an interesting question. So, I mean, one way is, of course, if we learn a policy network function, then this policy network function can be learned in way soft actor critic learns a policy network function. So like minimize the Kuiper-Glaber divergence to what like we represent as a sum of past Q functions. And then the sampling could be done from this policy network, of course. But we were discussing, so I'm not very familiar with this line of work, but I remember that we were discussing at some point that there is a way of transforming the discrete action policy into continuous action policy. So maybe Alex is more familiar with this line of work.
I'm not very familiar with it, but I think you're probably referring to like the Gumbel softmax trick.
Yes.
Which I think is used in other papers.
No, then maybe I'll send an email to ask about the other papers, because I only know what they do in soft actor critic, and then of course theoretically you can do some kind of Langevin sampling or whatever, but I've not seen anyone use that efficiently in practice.
And so for Gumbel softmax, it's something like we just I came across only during the last rebuttal on Clear when we tried to submit. It came up with during the discussion with one of the reviewer. So I think it's still something that we need to maybe check more closely. So I'm not sure I will give more details there.
No, well, thank you very much. Thank you for the very nice talk.
Thank you.
The question that I was wondering was, have you tried in practice without the weight correction? Like how much it impacts the performance between the vanilla and the weight corrected one?
I think, so thank you for your question. So I think for one of the iterations of the paper, we did this analysis, like not like analysis, we did empirical study of like, and in the end, there was not much difference because for large M, like they all look more or less like exact PMD.
Yes.
To some extent. But probably you will, we didn't perform it for small M flow. So maybe there is more to see there if we try like a smaller M choice.
Cool. And another things that I was wondering, if we take the case beta equal 1, so there is no entropy regularization. Let's take the case the vanilla one. You have this kind of approximation error would be beta power m, so this would stay constant, right? But I don't know if you have any intuition. I was thinking if I remove just one Q function, then maybe I expect that the error shouldn't be too big. So I was wondering if you have any idea that if beta is equal 1, you can still have an approximation that decreases with m, but maybe now polynomially and not exponentially. This is a bit of a guess, but I was just curious if you had any thought about that.
Okay, so to answer your question, so we didn't really analyze this case, but our paper, so like prior to this work, actually, we were analyzing Polytech paper, and we were actually in Polytech, it's essentially where beta is equal to 1. And we were trying, like to some extent, also implement this, the summation of the Q functions, but in the growing architecture way. And this work was presented in the WRL. We called it Cascade Neural Network. So it was such a mess to just like scale it to the large K. But I remember that by reading the original Polytech paper, like just empirically, they tried only 10, doing only 10 Q functions instead of all the Q function. And I think they were achieving quite good results, but it was a very limited evaluation, like only on 2 environments or something.
I remember.
So then in terms of analysis, theoretical analysis, so for me, it's basically this term that would be affected. Like if you choose beta equal to 1. So basically this becomes 1. And our penalization is somehow like, and this penalization, this like policy improvement is used in many, many other steps further in our proof. So for example, here, like to get the evaluation of this one, we actually apply here, we reuse our result of policy improvement because we know that CK plus 1, it's the sum of all the Q function. So we can somehow like, I don't know, telescope those differences of the sum. And thus those differences, in those differences, we'll get the sum of all the errors of penalization from the approximate policy improvement here. And thus, wait, I moved too much. So here, if beta is equal to 1, this will just start to scale as something as k, there would start to appear here the term depending on k, so number of iteration. So yeah, you will have a polynomial with k error. So which is so you will observe the accumulation of errors. So I don't think, at least in our framework, it's easy to consider beta equal 1.
Yeah. I think it's an interesting question. Thanks a lot for sharing your insights.
Well, but as we didn't dig too much further, I can't really give more details on that.
Yeah, I think probably if one would manage to look at the policy improvement lemma that you were showing and have something that decreases with m, even though beta is equal 1, maybe you can get something.
Maybe if so maybe not in vanilla maybe not vanilla version. So I think some kind of reweighting probably would be required in the summation of the Q function. So even in weight corrected version, so as here we divide by 1 minus beta.
Yeah, the weight would be infinity, yes.
Yes. So it doesn't make sense here either.
Cool, very, very nice. Any other question by the audience?
Yes.
No, I mean, I don't have a question, but I guess no one has a question.
Okay.
maybe we can stop the recording and see if someone wants to talk without recording.